Today at Autofixxpro, what should I select when stationary? D or N? Here you will find the correct answer to your question. What's going in D or N in the automatic transmission from ZF? N or D? What should I do? To understand this, let's take a closer look at the transmission. Here is an overview of the components again. You can find more videos about how the components work, power flow, and a video in which I partially dismantle the transmission on my YouTube channel, Autofixxpro. Assumption. Selector lever in position D. The vehicle is stationary with the brake pedal depressed. Brake A, brake B, clutch C are engaged. The converter housing and thus the converter's pump wheel are rotating. The turbine wheel is seated on the transmission input shaft via a gearing. The oil flow from the pump wheel enters the turbine wheel and attempts to drive it. Since the turbine wheel is stationary, this force, pressure of the oil from the pump wheel, is partially returned to the pump wheel. This back pressure causes the engine to require more power. In order to keep the idle speed constant, the throttle valve is opened further in gasoline engines, thereby increasing the injection quantity, and the injection quantity is increased in diesel engines. This would increase fuel consumption. In addition, the stationary guide wheel further increases the back pressure on the pump wheel. To understand what happens in the transmission in position D, you need to know the structure and function of the torque converter. There are already several videos on this topic on the internet. Here is a summary of the basic function. The pump wheel is firmly integrated into the converter housing. The converter housing always rotates at engine speed. This means that the pump wheel also rotates at engine speed. The turbine wheel is seated on the transmission input shaft via a gearing. The turbine wheel houses the dual mass flywheel and the inner disc carrier of the torque converter lockup clutch, TCLC. When the TCLC is closed, there is a direct connection between the pump wheel and the turbine wheel. The oil flows from the pump wheel into the turbine wheel and is deflected by the stator wheel in the conversion range. Conversion range means the pump speed is faster than the turbine speed. Let us now attempt to understand the processes in the transmission when the vehicle is stationary, the engine is running, and the transmission is in position D. When stationary, the transmission is in first gear. In some vehicles, second gear. The power curve in first gear is then shown. Let us now turn to the force curve in the transmission, explained using the sectional drawing. The force is applied via the drive shaft or transmission input shaft. This is connected to the turbine wheel of the torque converter via a gearing. When the turbine wheel of the converter rotates, the drive shaft rotates. The inner disc carrier of clutch C is located on another gearing of the drive shaft. When clutch C closes, the force is transferred from the inner discs to the outer discs, and thus to the outer disc carrier of clutch C. The outer disc carrier therefore rotates at the gearbox input speed, and with it the Sun Gear 4 connected to the outer disc carrier. In the first planetary gear set, brake A holds the Sun Gear 1 in place. At the same time, brake B holds the Ring Gear 1 in place. Since Sun Gear 1 and Ring Gear 1 are fixed, Planetary Gear Carrier 1 can no longer rotate and is therefore fixed in place. Planetary Gear Carrier 1 is connected to Ring Gear 4 via the large pot, which is therefore also fixed in place. The Sun Gear 4 thus drives the planetary gears in the 4 planetary gear set. The planetary gears roll on the fixed Ring Gear 4 and thus drive the Planetary Gear Carrier 4, which is connected to the output shaft, i.e., the transmission output shaft. The vehicle is driving in first gear. If we are standing at a traffic light and D is engaged, our transmission output shaft is stationary. This also means that the Planetary Gear Carrier 4, which is connected to the transmission output shaft, is stationary. As already explained, since the Ring Gear 4 is also stationary, the Sun Gear 4 cannot rotate either. Since the Sun Gear 4 is connected to the input shaft via the closed clutch C, the input shaft, and thus also the turbine wheel and the torque converter, cannot rotate. What does the transmission manufacturer do to reduce the increased load on the engine and thus the increased fuel consumption? The solution is called stand decoupling. Stand decoupling is used as soon as the transmission oil temperature reaches a certain range. For example, between 13 and 120 degrees Celsius for some automatic transmissions. How does this standoff disconnection work? Among other things, the vehicle receives information that it is stationary via wheel speed sensors. At the same time, the brake pedal switch sends information that the brake is applied. If the stand decoupling is active, brake B opens. Brake A and clutch C remain closed. This results in the following force curve. The drive shaft remains connected to the Sun Gear 4 via clutch C, which rotates at the gearbox input speed. Since the vehicle is stationary, the transmission output shaft and thus also the planetary gear carrier 4 are also stationary. This has the following effect. In planetary gear set 4, ring gear 4 now rotates in the opposite direction. This also causes planetary gear carrier 1, which is connected to ring gear 4 via the large top, to rotate backwards. Since the planetary gear carrier 1 thus rolls in the opposite direction on the held-in-place ring gear 1, the planetary gear carrier 1 also drives the ring gear 1 in the opposite direction. Since the ring gear 1 is not held in place by the open brake B, the ring gear 1 can rotate freely. No power is transmitted. The transmission input shaft thus rotates relatively freely. Only a low load is present, which is caused by the friction of the planetary gear sets and the drag torque of the open brake B. As a result, the slip or speed difference in the converter, i.e. between the pump and turbine wheels, is only approximately 20%. If the standoff decoupling were not active, the slip or speed difference would be 100%. The load on the motor is therefore reduced by approximately 80% compared to a non-existent standoff decoupling. To ensure delay-free starting after the standoff decoupling, the slip is not reduced to 0% by opening all clutches and brakes. In addition, an open brake or clutch has the disadvantage of creating additional drag torques, which in turn would increase the load on the turbine wheel and thus on the engine. This would also lead to further gear changes at every stop. This would place additional strain on the gear shift elements, i.e. clutches and brakes. Therefore, when stopping, for example at a traffic light, you should not shift to N. In position N, all gear shift elements are opened, which has the above-mentioned disadvantages. All modern automatic transmissions have a neutral disengagement feature. N is used in car washes, for example, because the neutral disengagement feature is not in use here, as the brake pedal is not being pressed. Therefore, use D, not N, when you stop your car, for example at traffic lights. Thanks for watching. Like and subscribe and leave comments. Would be great. Thanks.